In this video, we're going to look at energy cycles. Specifically, we're going to look at BORN-HABER cycles. So, lattice enthalpy is the amount of energy required to break an ionic compound into its gaseous ions. The definition for this is in section 18 of the data booklet if you forget. Here's an example. So sodium chloride solid breaking apart into sodium plus gaseous ions and chloride gaseous ions. And the enthalpy, the lattice enthalpy is 771 kilojoules per mole, and that's an endothermic reaction. So there are two things that influence lattice enthalpy. One of them is the charge on the ions, and the other one is the ionic radius. So if we take a look at the lattice enthalpies for magnesium oxide and sodium chloride, you can see that magnesium oxide is very high. It's almost 4,000 kilojoules per mole, whereas sodium chloride is around 790 kilojoules per mole. But part of that is because magnesium oxide has a much higher ionic charge than sodium chloride. Magnesium and oxygen both have charges of plus and minus 2 respectively, whereas sodium and chloride have plus and minus 1 respectively. The radius of the ions also plays a role. So if you look at the table here, we were looking at the ionic compounds, lithium fluoride, lithium chloride, bromide, iodide, and so on. So the lattice enthalpy decreases as the ionic size increases, as you can see in this table, because lithium would be, or fluoride would be the smallest and iodide would be the largest. And that's because of the reduced electrostatic attraction between the ions, because as the ion gets bigger, the force between the two is smaller because the nucleus is further away. So BORN-HABER cycles are used to determine the lattice enthalpy, and they account for the following. One, the enthalpy of formation. So that's the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. There's also the enthalpy of atomization, or delta H subscript AT. That's the enthalpy change when 1 mole of gaseous ions is formed from an element in its standard state. So you've got your sodium and then becoming sodium ions in its gaseous state. Making it in its gaseous state from an element in its standard state. Then the bond dissociation energy, that's the energy required to break 1 mole of bonds in the gaseous state. The ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms. So there's that one. And then finally, electron affinity, the energy released when 1 mole of electrons are added to 1 mole of gaseous atoms. So all of these things together can be taken into account to determine the lattice enthalpy. So this is a BORN-HABER cycle for sodium chloride, and you can see that all of the enthalpies are here. So if you take a look, some of them are endothermic. They have positive energies. Some of them are exothermic, like so. The lattice enthalpy here is endothermic. So to determine the lattice enthalpy, we do the following. If we start here, we always make this our starting point, because the delta H of formation will be endothermic, or exothermic, these ones are endothermic. So you start here, and if you go in this clockwise manner, we want to end up here. So you would take this, and then plus this, plus that will get you to that point. Or you can start here and go this way. So this plus this will equal that. So you can either go clockwise to there, or anti-clockwise to there. So let's talk about that. So if we take a look at that, we have this one plus this one plus this one plus this one. We end here. We start here. or this one plus this one, and we end here. So if we wrote that into a relationship, this plus this would equal all of those added together. So we could write that as an expression, and we'll do that up here. So delta H of formation plus the delta H lattice is equal to the delta H of atomization plus E plus the delta H of ionization plus the delta H for electron affinity. You could then rearrange to just solve for lattice enthalpy, so you would just put delta H lattice is equal to all of those things minus the heat of formation. So that's how you would solve for that. So now if we plug the values in, we'll actually prove that this relationship equals the lattice enthalpy. So our delta H of atomization was 108 plus 122 plus 494 plus negative 364 because the electron affinity was negative, and then minus the heat of formation, 411. That is equal to 771 kilojoules per mole, which is the value that we saw for the lattice enthalpy. So now let's find the lattice enthalpy for potassium fluoride. So again, we see our BORN-HABER cycle. So again, we're going to start here, move around, and then go this way. So this is going to be equal to this, plus this, plus this, plus this, and then minus this. So one thing to note, you can see here that this value is halved because fluorine is a single, or is a diatomic molecule, so we need to take that value, and it was already done for us, divided in half, because we want it for one fluorine atom. So I'm just going to solve it at the top so that we can keep referring to our numbers rather than flipping to a new solution slide. So our delta H lattice is going to be equal to the delta H of atomization, so plus 90 plus 79.5. So that value, if you were to look it up, would be twice that value, so you'd need to know to split it. Plus 419, and then plus negative 328, because that's exothermic, and then minus negative 569. And that all equals positive 829.5 kilojoules per mole. So you'll notice something different for the lattice enthalpy for calcium oxide. So remember, calcium and oxygen both, calcium has to lose 2 electrons and oxygen needs to gain. So there will be 2 ionization energies and 2 electron affinities for those ones. But you just solve it the same way. So you still start here, plus this, plus this, plus this, plus this, plus this, plus this, minus this one. So to solve that, I'll solve it at the top again. So the lattice enthalpy is equal to 178 plus 249 plus 590 plus 1145 plus negative 141 plus 798 and then minus negative 635. Let's make sure we didn't miss anything. 178, 249, 590, 1145 minus 141 plus 798 minus 635, and that gives us a grand total of 3,454 kilojoules per mole. And that's a positive value. So remember, we talked about how ion charge has a big impact on lattice enthalpy, and this just demonstrates that. So the first two, the ion charges were just plus and minus 1. These ones are plus and minus 2. And we have a very big lattice enthalpy. So now let's talk about the solubility of salts. So many ionic compounds are soluble in water. So when you add a salt to water, their lattices are broken and the ions are separated into their gaseous ions. So that is the lattice enthalpy. The ions are then hydrated as they get surrounded by water, and that's known as the enthalpy of hydration. And the sum of those two values gives us the enthalpy of solution. So if that enthalpy of solution is positive or negative, that will depend on whether or not the ionic compound is soluble. So if we look at the energy cycle for sodium chloride, you can see that the lattice enthalpy is here, right here, and it's equivalent to these two summed together. So these two are equivalent values. So to determine if something is soluble or not, if an ionic compound is insoluble, they'll have a high positive enthalpy of solution, so it won't dissolve. And then soluble ionic compounds have negative enthalpies of solution or a really low positive value. So we'll look at an example with sodium chloride where we will actually get a positive enthalpy of solution, but it will be so small it won't matter. It still will dissolve because we know sodium chloride is soluble. So here's our example from KOGNITY. So we're asked, given the following values, calculate the enthalpy of solution for sodium chloride. Well, that is just delta H of solution equals the lattice enthalpy plus the enthalpy of hydration. But remember, we have two enthalpies of hydration. So it's going to be equal to 790 plus negative 424 plus negative 359. So that's equal to plus 7 kilojoules per mole. So as you can see, it is positive, but it's very small. The value is very small, so this still would be soluble. So there are a few things that impact, or two things that impact the enthalpy of hydration. One of them is the ionic radius. So the larger the radius, the lower the magnitude of the enthalpy of hydration. So you can see that with these ions. So lithium is the smallest, but it has the largest magnitude of the enthalpy of hydration, and so on. The other thing that plays a role is the ionic charge. The higher the ionic charge, the higher the enthalpy of hydration. So you can see for aluminum 3+, the enthalpy of hydration is negative 4,741 kilojoules per mole.